All right, you crazy kids, here's your lecture on the gas laws. We have 5 different gas laws to get through today. Let's see how it goes. Our first one is Boyle's law. It's a pressure and volume relationship. That means the other measurable quantities of a gas are going to be held at constant, or N and T are K. Now, with pressure and volume relationship, what we're going to be thinking about is a balloon. I'm going to have a sample of gas in that balloon. If I increase the pressure on that balloon, all right, let's pretend like I put it in some type of chamber, or I bring it underwater, something like that, what's going to happen to its volume? Well, it would make sense that the balloon would decrease in size because of the added pressure on the exterior of the balloon. So as pressure goes up, volume goes down. This is an inverse relationship. The mathematical expression of that would be P1 V1 equals P2 V2. And these would be your initials on this side of the equation and your finals on that side of the equation. So the ones stand for whatever relationship I give you to start with. So, we have a balloon. It has, 2 atmospheres of pressure and 45 liters. And then the 2's would be the changes. So I take that balloon and I change its pressure to, 10 atmospheres. What's its new volume going to be? That's the type of calculation you're going to see. You'll have some practice problems on that. Our next one is Charles' law. It's a volume and temperature relationship, meaning pressure and number of moles are constant, the other measurable quantities of a gas. Let's think about what's going to happen on this side. So if I have a balloon, I have a sample of gas in it, and I increase the temperature on that balloon, the particles of that inside the balloon are going to start moving faster and faster and faster. However, I can't change the pressure, meaning they're going to have to collide with the walls of that balloon the same number of times. To make the same number of collisions, well, that's not a very good drawing, I would have to have a much bigger balloon with the same sample of gas. Meaning, as temperature goes up, your volume also has to go up in order to keep the pressure the same. And the number of moles, whatever sample of gas you have in that balloon stays the same. This is now a direct relationship instead of our previous example, which was inverse. So our mathematical relationship, is going to be T1 V1 equals T, oh boy. Almost messed up there. Actually, I did mess up, but we're going to pretend like I didn't. T1 V2 equals T2 V1. There we go. Sorry about that. Now, your initials are now opposite of each other. That's because we have a different relationship of our gases. So be aware when you're trying to calculate this. Another important fact, your temperature must be in Kelvin. Otherwise, you're going to get some negative volumes as you decrease your temperature. That would be very weird. So if you don't change your temperature to Kelvin, you will get these problems wrong. Make sure they are in Kelvin. Our next one is a pressure and temperature relationship. If it's pressure and temperature, that means number of moles and volume is going to stay the same. So instead of a balloon, which can change its volume, I would now have like a cube. Maybe it's a steel box. All right, and I have a sample of gas in that steel box. Now, if I increase the temperature on that steel box, meaning my particles are moving faster and faster and faster, what's going to happen to the pressure inside that box? Well, if my particles are moving faster and the size of the box can't expand, that means I'm having more collisions inside my box. Or as temperature goes up, your pressure also goes up. Once again, this is a direct relationship. So that's going to be P1, a couple of mistakes today. P1 T2 equals P2 T1. Once again, we have temperature involved, so your temperature must be in Kelvin. Be wary. Combined gas law. You're taking all 3 of these gas laws and combining them together into one giant gas law. This is, kind of what we're going to use more often than not, because chances are you can't really, keep all these variables at constant. So it's very difficult to have your temperature stay constant, your pressure stay constant, and your volume stay constant when you're using the Boyle's, Charles, or Gay-Lussac law. So we combine them all together. When we combine them all together, we're going to get P1 V1 T2 equals P2 V2 T1. This is the one that's actually in your packet. So you have that formula. However, the other formulas you don't have. Well, what are you going to do? How are we going to figure out, or how are we going to memorize these first 3 formulas? The trick is you don't have to. All you got to do is remove the variable that's not in the calculation, and you'll be left with the actual formula you want. For instance, if I have some calculation that mentions pressure and temperature, but doesn't mention anything to do with volume, I would simply remove volume. And there, we have a pressure and temperature relationship. Oh, that's the same formula that's right here. Same thing. Crazy. That's how it works. If that doesn't make sense, I'll have to explain it to you another time, but that's basically what you do. I want my original. Where is it? There we go. Cool. Now, Our more fun type of gas law is the ideal gas law. This is when you have a relationship between pressure, volume, temperature, and the number of moles of gas. However, you don't have like an initial and a final like you do on your first 4 examples. So like your initials seen in purple and your finals seen in red. Now you're going to be solving for an unknown. So you're going to be given the pressure, volume, temperature, number of moles of a gas, except one of these variables we don't know. You're going to use the other 3 variables to solve for that unknown variable. This formula is also in your packet. It's PV equals nRT. R is universal gas law constant. It's in your packet. It's not something you have to memorize. However, if you look in the packet, you don't just have 1 R, you have 3 R's. That's because those R's are dependent upon the unit of pressure. So you have to pick the correct R value in calculation to correspond with the right unit of pressure. That's because R is this magical variable that actually cancels out all your other variables. For example, if I had a pressure of 2 atmospheres, a volume of 40 liters, and a temperature of 290 Kelvin, I could actually solve for how many moles of gas I have because I have 3 of the 4 possible variables. So that would be PV equals nRT, and I can solve for n. So n would actually equal PV over RT. Now I need to plug all my values in and see how this works. So my pressure, 2 atmospheres. My volume, 40 liters. Value for R in this case is that I have to match the value that's with atmospheres. So it's 0.0821. And check out this unit. Liters times atmospheres over moles times K. Oh, what a crazy unit, but it's important. And then finally we have our temperature here, 290 Kelvin. Notice how I used a volume in liters and my temperature in Kelvin. That's because my unit for R cancels out those units. All right, so if I give you a volume and you're going to use the ideal gas law, oh my goodness, you're going to have to convert to liters. If I give you a temperature that's in Celsius, oh my gosh, you're going to have to convert to Kelvin. Everything must cancel out with the values in R, or actually the units in R. And we can see that here. Atmospheres cancels out, liters cancels out, Kelvin cancels out, and I'm left with 1 over 1 over moles, which is moles. What's the thing you're actually solving for? So be careful. Now, another cool thing with R is we have this idea of a standard molar volume. So if we see here, I have my standard pressure of 1 atmosphere and my standard temperature of 0 degrees Celsius. We call that STP, or standard temperature and pressure. If I plug those values in, I can get a standard molar volume. So PV equals nRT. Molar volume, what does that actually mean? It's how many liters per mole you're actually going to have. So I'm going to try to solve for is volume per mole. My volume per mole would equal, let's see here, RT over P. Now, if I have RT over P and I plug my values in, I'll have 0.0821 liters times atmospheres over moles times K. All right. My temperature for standard is going to be 0 degrees Celsius, but that's 273 Kelvin. And then my standard pressure is going to be 1 atm. If we look at our unit cancellation, ATMs cancel out, temperature cancels out, and I have molar volume, or the volume per mole. When I calculate this out, you're going to get a decimal, but it's really, really close to the actual standard molar volume, which is 22.4 liters per mole. That value is kind of important because any gas at standard temperature and pressure would always have the same volume of 22.4 liters if you have 1 mole of that gas. That is very important in chemistry. It's like this really cool thing you can do with conversions and calculations. I'll show you that too a little bit. But that is what we call standard molar volume. So any gas, well, we're going to write this down, any gas at STP has a standard molar volume, because that's standard temperature and pressure, of 22.4 liters per mole. That is important. All right, that's your lecture.